Hello guys, nice to see you. So let us recall what we learned last time. Tell me what is coherent light, and how we can get it in a simple way.
Because light is light with similar wavelengths,
The same wavelengths,
the same wavelengths, and in the increase.
constant phase. So how do we get it? Let's say if we don't have lasers, we can create such two coherent light sources.
We can use like prism to get monochromatic light, then use double split, to get
And then, well, there are some requirements. These slits should be small, so we can consider them as point sources of light. So we create some kind of spherical wavefront after light goes through these slits. And in that case, we will have monochromatic and constant phase shift two point light sources, which can be used to observe such phenomena as interference. What if we don't have a bracelet monochromator, which creates monochromatic wavelengths, like monochromatic illumination of the slit? What if we have sunlight and we just shine light on the slit? Would it be would be possible to consider these two slits as coherent light sources?
no, because visible light consists of different.
We have many wavelengths, and we will probably be possible to get some interference, but it will not be distinguishable because everything is mixed up with different wavelengths. So we indeed need this monochromatic light. So, what do you know about interference? What is physics background of this effect?
Waves are colliding. Something
They
like colliding.
interact,
They interact and amplify or destroy.
Okay, so that sounds more like with mechanical waves, but that's actually true also for electromagnetic waves. And since light is an electromagnetic wave by nature, if we have these two sources of coherent light, monochromatic and constant phase, they may interact with each other at given position, somewhere at some given point on the screen where we observe the interference picture. They may interact and result in different intensity. So either we have so-called constructive or destructive interference. What are conditions for constructive and destructive interference?
Phase difference between two wavelengths, two waves that interact with each other should be equal to 0 or be equal to 1 wavelength. Oh,
So
n
some integer number of wavelengths. So in that case, the phase shift is equal to 0 technically, because this phase shift of 2 pi means that it just equals to in terms of difference in waves, there is the case when in this given point of space at the screen, if we're talking about electric field, it's part of electromagnetic field, which actually defines the magnitude of the intensity of light. Then they will like amplify each other, so we'll get twice larger intensity in comparison to individual waves. And what about destructive interference? So then the phase shift should be
Zero.
like, so it should be like odd number of half of wavelengths, then they come in opposite phases, and obviously then they just compensate each other because they at the same time with the same magnitudes, but in electric field vectors are oriented in opposite directions. So these are fundamental aspects which we need to remember, and obviously we can define position of this constructive and destructive interference either via angle, some theta, so it's angular definition of their position, or linear, so we literally can, if we know angle and distance from the screen with two slits to the actual screen where we observe the interference picture, then we can provide some coordinate y or x and linearly define positions for this maxima and minima. So as a result of this destructive and constructive interference, the picture of interference looks like some alternating dark and bright fringes, which correspond to destructive and constructive interference respectively. During our discussion last time, we highlighted this fact that we cannot talk about just bright and dark. There is always some light intensity distribution. So when we claim that we have constructive and destructive interference, when we have phase shift exactly 0 or 180 degrees, then we are talking about the central parts of these fringes, bright and dark fringes, where we get maximum light intensity or minimum light intensity. So maximum light intensity corresponds to like doubling the light intensity because we have two waves, and minimum is literally 0 because they compensate each other. However, as we move a little bit further from the central parts of the fringes, we will see some variation in light intensity. So it will drop for constructive interference and increase for destructive interference. So our goal is to understand how this light intensity is distributed. And last time we already derived some equations, but let me refresh your mind. So we obtain an expression for phi, phase shift. So phase shift phi is equal to 2 pi over lambda times d, distance between two slits, times sinus theta. So that is the expression for phase shift, and we considered some resultant electric field at point P, which is the sum of electric fields originated from two coherent waves, light waves. So we have E naught times sinus omega t plus sinus omega t plus phi. So by applying um, trigonometric identity, we have shown last time that E naught, oh sorry, not EP, electric field at point P, will be equal to 2 E naught times cosinus phi over 2 times sinus omega t plus phi over 2. And here we consider that this is some amplitude value for electric. Maybe we can define it as EA. So amplitude value for electric field in this point. We see that amplitude value will be equal to 2 E naught if we have phi equal to 0, 2 pi, 4 pi, and so on. And E amplitude will be equal to 0 if phi is equal to pi, 3 pi, 5 pi, and so on. So if they are coming like these waves in 1 and E2 in phase, they result in doubling the strength of electric field, and in opposite phase, obviously, we get 0. So now, next step, tell me if we know electric field in electromagnetic wave. So that is some instantaneous magnitude of electric field, because obviously it changes over time. However, we want to first make a transition from instantaneous electric field to instantaneous light intensity, and then next step to some average light intensity is actually what our eyes as photo sensors work with. So our perception is based on the some average light intensity, and also all like other equipment like photo detectors also operate with some average light intensity. So light intensity is proportional to what in terms of electric field? So electric field in second power, E squared. So we know that. So we know that we can maybe write like this. Intensity is proportional to EP squared, electric field at point P in second power. And that will be equal to 4 E naught square cosinus square. Here will be phi over 2 sinus square omega t plus phi over 2. So that is distribution already of intensity, not just electric field. Now, as I mentioned earlier, we need to get some average. So average we can calculate within one period of time. So in that case, from previous discussions, we already know that sinus second power omega t plus phi over 2 over like one period from 0 to t, like average, will be equal to 1/2. If we integrate it all like from 0 to t and get average value, it will give us 1/2. So in that case, we can write that intensity will be already like averaged, will be I maximum, so maximum intensity, amplitude value, times cosinus square phi over 2. So we have this distribution for light intensity as a function of phase shift. So here we just introduce some constant maximum light intensity because here this is a constant. So if we integrate it over time, nothing changes because it's not function of time, some constant. Then when we integrate this part over time, like over one period and get average value, we get 1/2. So we just divide this constant by 2, and that will be some maximum light intensity. Not exactly because we see here that will be proportional. So here it's just electric field in second power. Uh, so in order to go from this expression divided by 2 to light intensity, we need to recall our previous discussions. But that's not so important now because we don't want to know the exact equation for light intensity now. We want to know how this light intensity is distributed. And we get maximum light intensity, which corresponds to double electric field because of constructive interference at uh, the same like in phase interference. And then we see that this will be a central part of the constructive interference fringe as a function of phase shift. So if phase shift is not 0, so that will be unity, so we will get maximum light intensity. If it deviates from 0, then there will be some distribution of light intensity. So now we know how we can express this phi, the phase shift. We wrote it here. So phase shift can be expressed in the following way. We can substitute it now in our final equation for light intensity. So if we operate with angular position of points on the screen, we can write that intensity will be equal to I maximum times cosine square pi times d sinus theta over lambda. So this is the distribution of light intensity in terms of angular position. And if we want to represent it in terms of linear position, we go for I maximum times cosine square phi times d over lambda L, capital L, which is distance between the slits to the screen. Oops. And we need to multiply it by y, which is position on the screen, linear position on the screen. So now we have these two equations which describe distribution of light intensity within the fringes, either constructive or destructive interference. So if we now switch to our slide, so this is how it actually looks. It's difficult to highlight clearly on the photo of the interference pattern. But we see that here in the central part is brighter than on the edges. And if we really have a very tiny photodiode and move it from one edge to another, and then go from bright to dark range, and then move further, like going from left to right, we will see that light intensity is distributed in this way. So we don't see such straight like square signal for light intensity for bright, so it's not uniformly distributed. We get to maximum at the center of the bright, fringe, and then it goes down according to those equations which we derived. So then here it goes to 0 in the center of the destructive interference and starts to increase as we move closer to next interference maximum. So we have such continuous distribution of light intensity. It's not just light on, light off. We have continuous distribution. So is it? Yes.
Uh, is it double slit or
So this is double slit. So if we go to cases when we have more slits than two slits, so this is the case for like double slit. You see we have this central part. It's a bit drops light intensity as we go from zero order to higher orders of interference maximum. However, if we increase number of slits, so that actually comes closer when we have many slits, like let's say 10 and more. First of all, as you see here, we get more complicated light intensity distribution in between maxima. So there are some small maxima and big maxima. So obviously analytical solution looks way more complicated. But the most important what you need to know that if we move to very large number of slits, then so-called resolution of this experiment, this interference, increases quite a lot. So why? Because as you may see here, what actually happens when we go from smaller to larger number of slits? This dark part, where supposed to be destructive interference, it gets broader and closer to zero. So it's not exactly zero because you see there is some signal, but it gets broader. So instead of having this smooth distribution, we have kind of abrupt drop in light intensities. And what happens with maximum? So this peak gets narrower and narrower. So instead of getting some broad distribution of light intensity here, we get this much narrower. And that actually helps to operate such multi-slit system as a diffraction grating, which we will consider a bit later, in order to use it in high accuracy optical instruments like monochromators, because we can use this grating in order to split white light in some spectrum. So why it actually happens? Because imagine you have this multi-slit system, you shine with white light, and each of the wavelengths will have some interference maximum. But since phase shift is a wavelength dependent parameter, we have shown in this in previous equations that phase shift depends on the wavelengths. Position of maximum for different wavelengths will be different. So in different points of the screen, we will see maxima for red, yellow, green, blue, and some UV light. And since they are so narrow, they will not overlap with each other. And that's why we will see, instead of bright and dark fringes, we will see red, yellow, green, blue color. Then it will be gap, and then again it will be another order of interference, like maxima order. Again, we will see the spectrum. This will not happen with two slit interference because they are so broad, this high intensity fringes, well, fringes of constructive interference, they will be broad, and that's why actually the same will happen. We will split light. This maxima will have different positions for different wavelengths, but since they are so broad, they will overlap with each other. And we will see just mixture of wavelengths, and mixture of wavelengths is actually our white light, what hits to this double split. And we will not be able to distinguish between different valencies and see different components, spectral components of the light which hits the double slit. However, when we increase number of slits, this maximum become much narrower. They will not interact, like overlap much with each other. We will clearly see the pattern of the spectral distribution of this white light. So coming back to my initial question at the beginning for discussion, if we have just double slit, then we will have overlapping of these maxima which are close to each other, and since the maxima are broad, they will overlap and we will not see any interference. However, if we go to large number of slits, the constructive interference fringes will shrink, and we will be able to distinguish closely located maxima of different colors. So in that case, we can use such system, which already becomes a diffraction grating. We can use it to split light into spectrum, white light into spectrum. And in all most advanced optical instruments, monochromators, instead of prisms, people are using diffracting gratings. But that will be more information about that a bit later. So this is the theoretical part, which is related to interference with at two slits, and also some general explanation what happening when number of slits is increasing. However, there are options to get monochromatic and coherent light sources, not only with having these two slits or multiple slits. Any ideas how we can create conditions for interference without two slits? So one option is reflection. If we have monochromatic light, so let's say this is a mirror surface, and we have some point source of light S. So what happens here? This is our screen. Maybe let's make it a bit shorter. This is the screen. So we have some ray goes directly to some point P, and another ray goes to the interface of the mirror. It's reflected from the mirror and hits the same point P on the screen. So what happens here? Assuming that this is monochromatic light, we can extrapolate this reflected ray, which goes to point P, and consider some imaginary light source S prime, which is placed at some distance d from the real light point light. So in this case, in this configuration, it looks like to the observer placed in this point P that ray 1 and ray 2, direct ray and reflected ray, originate from two different points, S and S prime. So that could be equivalent of double slit, because that's what we have. We double slit. There are 2 point light sources at some distance d. So in this case, all previous quantitative analysis will be applicable with only one difference. Any ideas what should be taken into account here, which is important for in terms of interference, in terms of determining the phase shift between ray 1 and ray 2?
I think there will be no phase shift. Just
Why?
what?
If there's no phase shift, there will be no interference. I mean, we will just get only maxima. So, but we actually, if we look at the screen, we will get the interference pattern. So it means phase shift will be. So in terms of geometry, it works as a double slit. Nothing different here. So there will be some different lengths of light path, which will result in phase shift, and it will be different for different position of points on the screen. However, here we have reflection, and that makes a difference. So need to know that if we have a reflection of light or any electromagnetic wave from more optically dense material, so we have air, and here we have some glass. So in this case, there is a phase shift of by 180 degrees when light is reflected. So incident ray and reflected ray, they are in the phase difference of 180 degrees. So taking this into account, that we get additional phase shift because of reflection from the interface with more optically dense material, conditions for constructive and destructive interference in this case will obviously change. So now it's kind of flipped over, because what was the initial condition for constructive interference when we have real two slits? So we need to have integer number of wavelengths. But now we have additional 180 degrees phase shift. So in this case, when we have integer number of wavelengths in fitting in the difference of path of two rays, we will get destructive interference, because they will eventually come in the opposite phases, since we have this opposite phase just because of reflection. And in order to get condition for constructive interference, we need to have odd number of half of wavelengths. Then they're supposed to be in phase, but on top of this, we get 180 degrees phase shift because of reflection, and this results in constructive interference. So these electromagnetic waves will actually arrive in phase. So that's why we need to consider that. Maybe we can write it here, but let's see how we define previously for d, d times sinus theta dark In this case will be m times lambda, and m is equal to 0, 1, 2, like plus minus. And d sinus theta bright will be m plus lambda over 2. So not lambda over 2, m plus 1/2 times lambda, where m is changing from 0, plus minus 1, plus minus 2. So this is a new condition for constructive and destructive interference. As you see, these guys are just opposite to what we introduced for interference when we have two slits. So the fact that we introduce additional reflection into this experiment, we need to take into account 180 degrees phase shift, and this fact swaps the conditions for constructive and destructive interference. So we will consider next time interference which occurs at thin films. So when we have a thin layer of one material on top of some substrate, and in that case, we also need to take into account this reflection from the interface between thin film and the substrate material. So that would also have impact on the conditions for constructive and destructive interference. So, summarizing our discussion. Yes.
How the phase shift is 180 when it comes to being.
So that can be explained quantitatively in the scope of the Maxwell system, the system of Maxwell equations, and it goes beyond the course which is discussed here. But the origin for this phase shift, the reason why it happens when reflection is actually occurs at the interface with more optically dense material, with what it means with material with higher refractive index. And so if we have air glass reflection, then we have this phase shift when light is hitting from air approaching glass and reflected. Then we have phase shift of 180 degrees. So this can be shown from the system of Maxwell equations. And what is important here to remember, when reflection happens from glass to air, so light is moving from glass to the interface with air and then is reflected, then this phase shift doesn't happen. So it happens only in that case when the reflectance happens at the interface with more optically dense material. So you just need to remember this. If you have any cases when the reflection happens from more optically dense material, you need to add this phase shift of 180 degrees or just 5. So during today's discussion, we continued this quantitative analysis of interference pattern, in particular light intensity distribution within light and dark ranges of interference pattern. So we clarify that it's not just some light on, light off. There is some light distribution. And how we approach that, we consider two electromagnetic waves with some electric field distributions as functions of time, with some phase shift P, which is described in terms of distance between two slits, wavelengths, and angular position of a given point on the screen. Then we sum up these two electric fields as functions of time and resulted in the expression for electric field in this some given point P on the screen. Then we made a transition from electric field to intensity, because intensity is proportional to E squared, and integrated it all like over the period in order to get the average intensity. So average intensity is like some equal to I maximum cosine uh, squared of phi over 2 phase shift as a function of phase shift. When we have exact in phase, we get the maximum light intensity corresponding to doubling the magnitude of electric field. When we get out of phase, so in opposite phases, exactly, we get just zero, because in that case, we don't get any light intensity, since waves compensate each other, electric vectors. Then we have shown that there is some distribution according to this cosine dependence along the screen. And what is important, if we increase number of slits, obviously analytical solutions will become more complicated. But the most important, what you need to remember, first of all, the dark fringes, they will broaden, and the bright fringes will shrink. And this position of bright fringes will approach the central position of bright fringes in case of just two slit, like double slit interference. So that feature allows us to distinguish interference maxima of different wavelengths which present in white light. So we can hit these multiple slits with white light, and because of narrow maxima fringes, we will be able to see the color distribution originated from splitting of this white light into a spectrum. So we go red, yellow, green, blue, and so on. So this is the pattern which applicable for diffraction gratings, to be discussed a bit later. What is also important to highlight, there are other options to create conditions for interference. We considered one with reflection, when we create kind of imaginary point source of monochromatic light. However, in this case, conditions for constructive and destructive interference, they kind of flip over, because of the phase shift between incident and reflected ray when we have reflection from more optically dense material. So this you need to keep in mind. Other from that, everything is the same according to our equations we derive for regular double slit interference. Okay, thank you very much for attention. See you next time, and we will finish our discussion of interference.